Okay, so in this section, we are going to talk about describing quantitative data with numbers. Okay, so after we're done with this section, you'll be able to measure the center with the mean and median and decide which is the best measure of center, measure the spread with the standard deviation in the interquartile range, decide which is the best, identify outliers mathematically, and construct a box and whisker plot using the 5-number summary. Finally, you'll be able to calculate numerical summaries with your graphing calculators, which some of you may already know. Okay, so when we take a look at SOCs, portion of our SOCs is measuring the center. The most common measure of center is the mean, or the arithmetic average. To find the mean, what you do is add up all of your observations and then divide by the number of observations you have. In statistics, the mean is going to be X bar. So think about you're holding all of your data to a certain bar or a certain standard. What bar should you hold it up to? You should sort of hold it up to the average. So you're adding up all the observations. Little n is dividing by the number of observations that you have. X1 is just your first observation. X2 is your second observation, all the way up to the total number of observations that you have. So in math, we like to shorten stuff, so we use the Greek letter sigma, is short for add them all up. So the formula for the mean is written like this. X bar, which is your mean, is equal to sigma x sub I. So that just means add up all of your observations, observation 1, 2, 3, 4, 5, divide by the number of observations that you have. Okay? I always want you to think about the mean as the balance points of your distribution, okay? So if think of a teeter-totter, it would be where you were balancing in the middle. Do you think if you have an unusually large or unusually small numbers, will that have any sort of influence on the mean? We're going to take a look at that in a later section, but I kind of want you just to keep that in the back of your mind. What will large or small numbers do to our mean? You will see two different symbols for mean. Let's just say we wanted to examine the AP exam scores for the AP Statistics students in Fairfax County. We just talked about X bar. So what does X bar really mean? That is specifically a mean taken from a sample. So we're going to define our population to be all of the AP Statistics students in Fairfax County. X bar is going to be the sample of AP Statistics students. So let's say that we get 20 students from various schools in FCPS, find the mean score for the 20 students. That is going to be X bar. Now, what happens if we get all of the scores of all of the AP Statistics students in Fairfax County? That is the mean taken from the population. That population, when we find the mean of a population, that is denoted as mu. That's when we got all of the scores of every AP Statistics students in Fairfax County. It's the population mean. X bar is the symbol, is the sample. The symbol is very, very important. Please, on your homework, tests, and quizzes, do not just write the mean is. Make sure you're specifically writing the mean of the distribution, or write X bar so we know specifically that it's from the sample, or mu that it's from the population. Okay, so notation is really important, especially as we move on. You're going to have to decide, is the information you have from a sample or from a population? So the other measure of center that we talked about was the median. You've heard of this before. So the median is just the midpoint of the distribution. What is the number in the middle? So the median is the midpoint of the distribution such that half of the observations are smaller and half of them are larger. To find the median, you've done this before, make sure you arrange your observations from smallest to largest. You can do this by hand, or you can do this on your graphing calculator. If the number of observations is odd, the median is the center observation, the one in the middle, equal number of observations above, equal number of observations below. However, if it's even, the median is the average of the two centered observations in the ordered list. Okay, so if we have 20 observations, observation 10 and 11, 10 has 9 below, 11 has 9 above, you would take the average of 10 and 11. That would be your median, or your middle. So let's just take a look at the data below to calculate the mean and median of commuting times in minutes of 20 randomly selected New York workers. Now before you do this, think about, what symbol am I going to use? Am I going to use X bar, or am I going to use mu? Well, since it's only 20 randomly selected New York workers, I'm going to guess that's not the population of New York City workers. That's just going to be your sample. So remember, when you're doing the mean, to write it as X bar. What bar are we holding it up to? So to find X bar, we're adding up all the values and dividing by n, which is 20. If you're asked to find the mean, you will have to show your work. You don't have to write out all the numbers, but you would just have to write out 10 plus 30 plus ... up to 45. That's only if you're asked to show your work. So the mean commuting time, the average commuting time, is 31.25 minutes. Let's look and see how this differs from the median. So in this case, I just made a stem and leaf plot to display them so I could sort of get an idea of what that distribution looks like. Okay, I included a key. I know that since there's 20, observations 10 and 11 are going to have 9 below it and 9 above it. So 20 and 25 are observations 10 and 11. How do I find the median? Add 20 plus 25 divided by 2. That gives me a median time of 22.5 minutes. These differ by about 10 minutes. That's a lot of time when we're talking about the measure of center. So which one of these two is going to give us a better measure of center? Okay, so the mean and the median are both measure the center, but in different ways. Both are useful. We just have to decide for our given situation which one's more useful. So the mean, remember, is always the average. And the median, think of that more as like the typical or the average value. Or no, sorry, think of it as the typical value. So the median is not the same as the mode. Remember, the mode is where most observations occur. However, the median is going to be somewhere around where most of the observations occur, whereas the mean can sort of be pulled along by higher values or pulled along by lower values. Just make sure you don't confuse the median. The meaning of the mean and the median. The median is physically the middle of the data, and the mean is the average, adding them all up and dividing by how many observations you have. Okay, so how can we compare the mean and the median, and how do we know which one is the best measure of center? The mean and median of a roughly symmetric distribution are going to be very close together. Okay, so if the distribution is symmetric, the mean and the median are both going to be in the middle. If the distributions are exactly symmetric, the mean and the median are exactly the same. Okay, this in real life situations, they're never going to be perfectly symmetric, but in a perfect world, if they were perfectly symmetric, the mean and the median would be the same. In a skewed distribution, so think skewed right or skewed left, the mean is usually further out in the longer tail than the median. So think about those means, okay? It's the average. If I have a distribution where I have a really long tail on the right-hand side, okay, so the mean is going to be pulled up by those values on the tail. I'm going to be adding a really large value at the end and dividing it, so it's going to make my mean bigger. Whereas the median is still going to lie where most of your values lie. If you have a left-tailed or a left-skewed graph, okay, your mean is going to be pulled down by those smaller values. It's going to be closer towards the tail, and the median is actually going to be more where most of the values lie. Okay, so if we think about our graph of our commuting times, was that skewed or was it about approximately symmetrical? Okay, so looking at the distribution and the mean and the median values, which is a better measure of center? If we were to look at our distribution of our commuting times in New York City, we had X bar, or our mean, was 31.25 minutes. In this specific case, the median is going to be a better representation of the measure of center. Look at where most of the values lie. Most of the values are between 0 and 45 minutes. However, the mean is pulled up by these travel times that are 60, 60, 65, and 85. So it's going to make the mean or the average time look larger than it actually is. Think about this. If I were to change the last travel time to 600 minutes, the median wouldn't change, but the mean definitely would. The median would still be in the same position, but instead of 85, I would just have 600. So then it would make the mean commuting time look much larger than it actually is. So in this case, the median of 22.5 minutes is going to be a better representation of how long people commute in New York City. Okay, so, and think about where the median is. It's sort of where most of the data lies versus 31.25, which is up in here, which is getting to the higher end of the data. So since the median is not going to be changed by that last travel time, it is said to be resistant to outliers. So what does that mean, resistant to outliers? That means the median is not going to change very much when I have either a really high outlier or a really low outlier. So if I take this 85, replace it with 600, absolutely not going to change my median. It's going to stay exactly the same. So how do I know which one to use, the mean or the median? If you have a graph that's roughly symmetric, you want to use the mean because that's mathematically the average time. Or if you have one that's skewed right or left, you want to use the median since it's resistant to the outliers. It's not going to be changed by a few large values or a few small values. So here's just a visual representation, okay, of knowing when to use the mean or the median. So if it's symmetric or roughly symmetric, the mean and median are approximately equal. So look at your symmetric distribution. The mean and median are both going to be in the middle. If your graph is right skewed, so skewed to the right, the mean is might. Okay, so if it's skewed to the right, the mean is might. However, I think it's sometimes hard to remember that the mean is greater than the median. So what I do is I draw my right skewed graph. I draw right down the middle of it, the median. Okay, so usually where most of the values lie, I draw a line. That's going to be your median. And then I draw the mean where the tail is, because the mean is going to be pulled up by the tail. Then it's very easy to see that the mean is going to be larger than the median. With a left skewed graph, left skewed mean is less, okay, than the median. If you don't want to memorize that, okay, once again, draw your graph where most of the data lies, okay, draw a line, that's your median, okay, and then draw your mean in the tail because your mean is going to be pulled down by those smaller values. So in this case, it's easy to see, okay, I drew a picture, the mean is smaller than the median. I don't have to memorize it, I've drawn it, and I can figure it out. Okay, so if a distribution was symmetric, the mean and median can both be used. However, most of the time you are going to use the mean. That's what you'll see. If a graph is skewed right or left, the median will be used to describe the center since it's resistant to those extreme values. And it's resistant to the extreme values, and it's going to be where most of the data actually lies. Okay, so just a little comic to think about your measure of center. So in retrospect, Jack was bragging about the mean height of his beanstalks rather than the median. So the median beanstalks would be much smaller, but it is resistant to outliers. However, the mean is not, so he's going to look like his beanstalks are much larger than they should be. Okay, so let's talk about the spread for a minute. So you've heard of the interquartile range, or the IQR. So a measure of center alone can just be misleading. So that's why we use SOCs when we describe a distribution. We want to talk about where the center of the distribution is, but we also want to talk about the spread. Is the data really closely bunched together, or is it really far spread out? So think about commuting times to New York City. Okay, maybe if you live in the center of the city, or in the city, the commuting time is going to be short because you can get in a cab, or you can take the train, or you can walk, versus someone that lives far out in the suburbs, it's going to take them a lot longer. So a useful numerical description of a distribution requires both a measure of center and a measure of spread. This comes from our SOCs. So how do we calculate the quartiles in the interquartile range? Hopefully you've done this before. So to calculate your quartiles, arrange the observations in order, locate the median. Okay, draw a line down. The first quartile is the median of the observations located to the left of the median. So you put your median in the middle. Quartile 1 is the median of the lower half. Quartile 3 is the median of the upper half. So if your median in the middle, then you find the median of the lower half, quartile 1, median of the upper half, that's quartile 3. The interquartile range is going to be quartile 3 minus quartile 1. So it's basically the upper quartile minus the lower quartile. Okay, so also think about this. So you've divided your graph in half, All right, so that you have 50% and 50%, and then you've divided it in half again. So now I have 4 pieces, which means I have 25% goes up to quartile 1. From quartile 1 to the median is another 25%. From the median to quartile 3 is 25%, and from quartile 3 to the end is 25%. So quartile 3 to quartile 1 is going to be where 50% of your data lies. Okay, so let's find and interpret the IQR. So interpreting is very important to understand what that means. Interpret always means you have to put it in context and be able to give this piece of paper to somebody walking down the street. They'll read it and understand what you're talking about. So here's our travel times for our 20 randomly selected New Yorkers. Okay, so what we did first was we found the median. Okay, so first we put them in order from lowest to highest. Okay, our median was right here, so that's the middle between 20 and 25. Okay, then, okay, so we drew a line straight down the middle. So we had 10 observations below and 10 observations above. So then our quartile 1 is going to be observation 4 and 5. So there's 4 below and 4 above. Okay, and then over here for our third quartile, same thing. We're going to find our median values. Okay, so we said our median was 22.5. Our quartile 1 is going to be 15 because it's the middle of these two 15s. Quartile 3 is going to be 42.5 because it's the average of the two middle numbers, because I had 10 observations below and 10 observations above. So 40 and 45, you had 4 above 45 and 4 below. Sorry, 4 above 45 and 4 below 40. Going down to here because this is my median. Okay, so the interquartile range is just Q3 minus Q1. So interquartile range, we said 50% of our data, here's 25%, here's 25%, here's 25%, and then the next 25%. So the interquartile range, the middle 50% is 27.5 minutes. So what does that interpretation look like? So the interpretation is the range, or you could say the IQR, the range of the middle 50%. That is really important because you want to tell the reader exactly what you're looking at. So the range of the middle 50% of the travel times for the New Yorkers is 27.5 minutes. So the middle 50% only ranges 27.5 minutes. Is the range resistant? So the travel times, once again, to work for the 20 randomly New Yorkers are written below. Okay, so we found our IQR was 27.5 minutes. Is our range resistant to outliers? Is it going to change if I add a high or a low value? Okay, the range is not resistant to outliers because I have here the range is from 5 to 85. So that's a 80-minute range. If I add that range of 600, that's going to say that the range is 595. That's huge. That is not resistant. That changed a lot. However, the IQR is resistant to outliers because when I add that high value of 600 over here, it's not going to change the IQR. So the IQR and the median are both resistant to outliers. Okay, so the other thing that the IQR is important for is it can help us to identify our outliers. So we talked about the center, we talked about the spread, now let's talk about outliers. So how do we find an outlier? So we take 1.5 times the IQR in order to find our outliers. So we call an observation an outlier if it falls more than 1.5 times the IQR above the third quartile or below the first quartile. On the AP exam, your homework assignments and your test, if you're asked to find outliers, you must show your work. If you don't show your work on how to find the outliers and you're graphing a box and whisker plot, which we'll talk about in a minute, then you will get points taken off. Okay, so let's take a look at the New York travel time data. We said that Q1 was 15, Q3 was 42.5, and the IQR was 27.5. So the Q3 minus the Q1. So what points on our New York travel times are going to be outliers. So what you do is you take 1.5 times the IQR. So 1.5 times 27.5 is 41.25. So it's an outlier if it's 41.25 above the Q3 and 41.25 below Q1. All right, so we're going to take quartile 1 minus 1.5 times my IQR, so 15 minus 41.25 gives us a negative commuting time, not even possible, obviously not an outlier. However, if I take Q3 plus 1.5 times the IQR, so this is the math you want to show right here, okay, the 42.5 plus the 1.5 times IQR, we get 83.75. And that tells us anything above 83.75 is actually an outlier. So if we look at our data, did we have an outlier? At 85 we did. So if it said to interpret it, it would mean any travel time shorter than negative 26.25 minutes, which doesn't even make sense, or longer than 83.75 minutes is considered an outlier. Okay, so if we took a look at our data, the only outlier we had was that 85 guy. So he did pull our average up. Made the commuting time look longer than it actually was. Okay, so what is the 5-number summary? You're going to often hear, please include the 5-number summary. What is it? So the 5-number summary basically just gives us our basic information of our data. Okay, it gives us the minimum and the maximum values. They tell us a little bit about the distribution, but the median and the quartiles tell us a little bit more about the tails of the distribution. Okay, so they tell us, is it really far spread out? Is it not so spread out? So to get a quick summary of both the center and the spread, we're going to combine all 5 numbers. So the 5-number summary of any distribution is your minimum, your quartile 1, your median, your quartile 3, and your maximum. So it shows us the highest values, the lowest values, and quartile 1 to quartile 3 gives us our middle 50% of our data. Okay, so what is the goal of the 5-number summary, and what are we going to do with those numbers? With those numbers, what we're going to create is we're going to create a box plot. Now keep in mind that a box plot is only for quantitative data. Hopefully you guys remember how to make box plots from the past. Your box plots in statistics are going to be just a smidge different than the box plots you have previously done. So I'm going to quickly go through how to do them, and keeping one thing in mind. There's something as part of our 5-number summary that we've looked at that we haven't looked at previously, and that's outliers. So our box plot, please make sure that your box plot are always showing your outliers, and as a reminder, you always need to show your calculation for your outliers. All right, so how exactly do we make a box plot? Step 1, we need to calculate the boundaries for the outliers. Make sure you show your calculations. 2, draw and label a number line that includes the range of the distribution. So lowest number to highest number, make sure they're evenly spaced and you show what each of your lines represent in terms of numbers. You draw a box from Q1 to Q3, so that's, remember, the middle 50% of your distribution. You make a line where the median is inside the box, so you know that 50% of your data is above the median, 50% is below the median. And then you extend lines or whiskers from the box out to the minimum and maximum values that are not outliers. Okay, so if you do have an outlier, you extend the whisker from Q3 to the boundary for the upper outlier, and then past that you would put the dots for your outliers. And then to get your lower bound, if you have a lower bound outlier, you would draw a line from Q1 down to the lower bound for the outlier, and then your lower bound outliers would be below that, represented as dots. Okay, this is going to be called a modified box and whisker plot, and it's modified because it's specifically showing our outliers. Make sure you show your outliers as dots on the graph. So remember, we always want to present our information to someone looking at our data, and they would very clearly be able to see, okay, well, these couple points are outliers, so we know that they're going to affect our mathematical calculations, specifically the mean. Okay, so let's make a box plot of our New York travel times data. So first of all, remember to put your data in order from least to greatest. All right, we already calculated the quartile 1 to be between the two 15s. We calculated the median to be 22.5 and the quartile 3 to be 42.5. All right, so if you notice, so 15, here's our lower whisker. Okay, here's quartile 3, or quartile 1 at the beginning. Here's our median. Here's our quartile 3. And then notice how the whisker is extended out to where the boundary for the upper outlier is, and this dot over here is going to be our upper outlier. Okay, so we have our minimum right here, quartile 1, you have your line, median down the middle, quartile 3, upper edge over here, the maximum. Okay, now notice how this end of your whisker does not extend to the maximum because the IQR, the 1.5 times the IQR, gave us the boundary for the outlier. Okay, so this is just going to extend to the largest value before the outlier. So we said that 85 was the outlier, so it's just going to extend to 65. Okay, and then our dot is going to be where the outlier is. It doesn't extend to the boundary of the upper bound of the outlier. It extends to the value before the outlier. So just keep that in mind. Okay, so what are some common errors when we talk about box plots? All right, first of all, do not refer to the box in the middle as the IQR. So don't just say the middle of the box plot is the IQR. We found the IQR by subtracting Q3 minus Q1. It's specifically a number. It is not the box itself. It is the length of the box, and it tells us where 50% of our data lie, specifically between two numbers. Also, I know that we haven't talked about this really yet, but do not ever state that a box plot is approximately normal. All right, when we talk about box plots, we specifically say that they're symmetrical. Well, what does it mean if they're symmetrical? It means the median is in the middle of the box, and the whiskers are about the same length. Now, just keep in mind that nothing is ever going to be perfectly symmetrical, so the median might not be right in the middle of the box, but by looking at our box and our whiskers, if it's symmetrical, the median will be about in the middle and the whiskers will be about the same length. Okay, so if we look at this one, I would actually say, if you take a look at the median, it's not quite in the middle, and there's a long right whisker and a shorter left whisker. So this would indicate to me that the travel time is going to be right skewed. Well, how does that tell us if it's right skewed? It indicates that it's right skewed because we have a long right whisker, just like I would have a long right tail. Okay, so I was just talking about how the box plot was right skewed. How exactly can we tell what the shape of a graph can look like from a box plot? All right, so here is an example of a graph that is right skewed. All right, what does the corresponding box plot look like? Well, if you look, we've calculated where the lower quartile is. Okay, so there's quartile 1. We're making the box plot based on this data. All right, here's the median of my graph. Notice where it is in my box. It's right here. It's closer to the left-hand side. Here's my upper quartile. And then notice how I have this long right tail. All right, so I have this long right tail. So take a look at the right whisker. So this says that 25% of the data is pretty spread out. And since 25% of the data is pretty spread out, that's going to say that our box and whisker plot is, and the shape of our graph is going to be right skewed. I have a long right whisker, and if you notice, the median is not in the middle of the box. All right, it's more towards the left-hand side, because remember that the median is going to be around where most of your data is lying because it's a typical value, and since it's a typical value, it's going to be where most of your data is. So this indicating over here that 25% of your data is between between 0 and 2, that there's a lot of data on the left-hand side of your graph, which means it's going to be right skewed. Okay, so the histogram was skewed to the right, the box plot was skewed to the right. How could I tell? There was a long right whisker, which indicates a long right tail. Okay, so what is my box and whisker plot going to look like if it is left skewed? All right, so sort of the same thing. Here's your minimum value down here. This is going to be where our quartile 3 is. Our median, okay, our quartile 1, our median, our quartile 3, and then our upper value. But if you look at your histogram, you're going to notice that there's a long left tail on your histogram, and in your box plot that's indicated by a long left hand side whisker. So that's showing that 25% of your data has a pretty large spread. Okay, so if a histogram is skewed to the left and a box plot is skewed to the left, you'll know that by taking a look at the long left whisker, which indicates a long left tail. Okay, so let's get a little bit of practice with some box plots. So below is the data for income in thousands of dollars for 12 households. All right, so here's what I would like you to do. After I've given you the directions, just take a minute and pause the recording. 1, please find the 5-number summary for the data. 2, calculate the IQR. Always show your work. Make sure you then interpret this value in context. So see if you can remember how to do that. 3, draw a box plot of the data. Make sure you show the work for the outliers. Even if there are no outliers, you need to show the work and then state there are no outliers. And then I want you to make the decision, would you use the mean or the median as a measure of center? So just take a second, pause the recording, and then take a look at the answer on the next slide. Okay, so first of all, your 5-number summary, you can get this from your graphing calculator. So if you need to, please go on the calculator instructions section and get the instructions on how to find the 5-number summary from your graphing calculator. Once you put the data in, it should be under 1 var stats, okay, just as a reminder. And also, the instructions will show you how to use a modified box and whisker plot on your graphing calculator instead of the normal one. All right, so you should have gotten the 5-number summary. They're listed here. Okay, your IQR, show that work. 317 minus 303. Q3 minus Q1 is 14 pounds. So what does that mean? Interpret means tell me in context what that means. The range of the middle 50% of the data is 14 pounds. So it is 50% of the data. So when you interpret the IQR, make sure you always state the range of the middle 50% of the data is blank in context. Okay, here's your box and whisker plot. See the work for the outliers. So here's your 1.5 times your IQR. So your Q1 minus that calculation tells you your lower bound is 282. 317 is Q3 plus the 1.5 times your IQR is 345. Now notice your box and whisker plot does not go to 345. That whisker, it goes to the largest value before the outlier. Okay, so we did have one outlier at about 360. Okay, if we take a look, now do we want to use the mean or the median? In this case, I would probably use the median since it appears to be slightly skewed to the right. Okay, I have my right whisker is a little bit longer than my left, but it's not huge. Keep in mind that choosing to use the mean or the median, sometimes it's okay to say, oh, I'm choosing to use the mean because the graph looks approximately symmetrical. The right whisker appears to be a little bit longer, but I think it looks pretty symmetrical. That's okay to have a different answer than I do, but just make sure that you can justify it. Why did you choose the mean over the median? All right, so please make sure that you go to the calculator directions folder to get instructions on how to create a box and whisker plot along with the 5-number summary on your TI-84 and TI-89 graphing calculator. Please make sure that from now on you're using the modified box and whisker plot, not the regular box and whisker plot. All right, so how are we going to measure the spread? So we've talked about measuring the center. How are we going to measure the spread of our data? Well, we've looked at the range, but there's another one that's better, and that's the standard deviation. The most common measure of spread looks at how far each observation is from the mean or the average. So remember, our average is sort of the bar that we're holding everything to, okay? That gives us sort of a point in our data in which to base everything else off of. Was it above the average, below the average? This measures the standard deviation. So let's just take a minute and explore it. I know that some of you have done this in Algebra 2 before, so this is just a quick refresher. So take a look at the data on the number of pets owned by a group of 9 children. So we made a dot plot of our data. It sort of appears to be right skewed. I kind of have a long right tail. Okay, I don't have a ton of data. So the first thing I want to do to find the standard deviation, or how far something is from the mean, is I first have to calculate the mean. What is the mean number of pets? And then we're going to calculate the deviation. How far is each data point from the mean? Okay, well, the deviation is the observation minus the mean. So if I figure out what the mean is, the deviation says how far is it from the mean. So if I take 5 minus the mean, that would tell me how many pets I am away from the average number of pets. All right, so in this case, our x bar, or the average number of pets, is 5. Okay, so if I wanted to figure out how far the deviation is from 1, I would take 1 minus 5, which gives me -4. All right, so it tells me that this is 4 pets below the average. If I wanted to take a look at 8, I would take 8, that's the number of pets somebody has, minus the average, which is 5, that gives me 3. That tells me that I have 3 pets more than the average. Okay, so how exactly are we going to measure the spread using the standard deviation? What does standard deviation mean over just regular deviation? All right, so each of our data points here represent how many pets the 9 people had. We first calculated the deviation, or how far they actually were from the mean. All right, so when we did the 1 pet minus the average of the mean, I got -4, so they were 4 below the mean. With 8, we said they had 8 pets minus the average, gives us 3. They were 3 above the mean. All right, so to calculate the standard deviation, number 1, the first thing we're going to do is we're going to figure out how far they are from the mean. Then we're going to square it. Okay, so we have all positive values. So 3 minus 5 is -2. Square that, gives you 4. All right, so how far are they from the mean? Then what we're going to do is find the average squared deviation. Well, what does that mean, the average squared deviation? So here's all your deviations, how far you were from the mean squared. We're going to sum those up and get a value right here. Okay, then once you sum that up and get a value, we're going to divide it by n minus 1, or the number of data points we have minus 1. This value is called the variance. Okay, so the average squared deviation is called the variance. So this 52 comes from adding up 16 plus 4 plus 1 plus 1 plus 0. Okay, that's 52. We had 9 students minus 1, so that's n minus 1 divided by 8 gives me 6.5. This is the variance. Now, really, we're not going to be using the variance too often. The variance really is just giving us information in order to find the standard deviation. Then to find the standard deviation, we take the square root of the variance. Okay, so we're going to take the square root of 6.5, which is 2.55. Okay, so what does that give us? So kind of think about it this way. In this sense, we squared it, and the reason we squared it was to make all of the values positive. And then when I take the square root of it, that is giving us the average distance from the mean. So on average, okay, the standard deviation says that we have 2.55 pets deviate from the mean. Okay, so on average, people have 2.55 pets more than the mean, 2.55 pets less than the mean. Okay, so the standard deviation just tells us the average of the distance from the mean, because we calculated the distance from the mean here in your column. Okay, so how do we interpret the standard deviation? We found this number. What does that mean? All right, so when you're asked to interpret, make sure you always put it in context. So what does it mean to interpret the standard deviation? The number of pets vary by 2.55 from the mean number of pets owned by children, which is 5. All right, so here is my 5 right here. So the number of pets vary, how far are they from that mean, by 2.55 pets. So on average, they have 2.55 pets more or 2.55 pets less. So it's how far on average they vary from the mean. Okay, this symbol right here, at the bottom, is your population standard deviation. So when you use your calculator, all right, you should always use the sample standard deviation for the standard deviation unless you know that the data are from the population, which is rare. Okay, so just your symbol for your variance. Notice how this is S of x squared. So that's showing you that this is the sample variance. Okay, notice the x1 is just saying that this was your data value minus the mean, squared it, plus your data value minus the mean, squared it. Adding all of those together, that's what your sigma means. Okay, I took the data minus the mean, squared it, added it all up together, and then the 1 over n minus 1 just says I divided that by n minus 1. Okay, so what's important about the standard deviation? Number one, the standard deviation, so small s of x, remember that is going to be your sample, measures the spread about the mean and should only be used when the mean is chosen as the measure of center. Do not use the standard deviation when you're talking about the median because the standard deviation doesn't say how far you are from the median or the middle, it says how far you are away from the average. Okay, the standard deviation is always going to be greater than or equal to 0. All right, so if the standard deviation is 0, then there's no variability. It means everything is stacked on top of each other. They're not spread apart at all. Okay, this would be when all of the observations have the same value. Think about this. The more spread out the values are, the larger the standard deviation because they're going to be further from the mean. The standard deviation has the same units of measurement as the original observation. So if we're talking about the number of pets, the units would be number of pets. The average distance from the mean is 2.55 pets. Okay. Now the standard deviation is not resistant to outliers. So a few outliers can make the standard deviation very large. So just keep that in mind. Okay. So the reason it's not resistant to outliers because it's based on the mean. The mean is not resistant to outliers, so the standard deviation is not going to be resistant to outliers. So if our mean is pulled up by a really high outlier, then so is the standard deviation. Okay, so how do I know which measure of center and spread to use? Okay, we have a choice between two descriptions for center and spread. You're going to group these two together. If you use the mean, then you're going to use the standard deviation, okay, because the standard deviation is calculated from the mean. If you choose to use the median, then you're going to use the interquartile range for your measure of spread because that describes where 50% of our data is lying. All right, so the median and the IQR are usually better than the mean and the standard deviation whenever we have a skewed distribution or a distribution with a lot of outliers, because remember, the mean and standard deviation are not going to be resistant to those outliers. We want to use the mean and the standard deviation only for reasonably symmetric distributions that don't have outliers. Okay, so about symmetric distributions. Skewed a little bit is okay, but about symmetric. Okay, just a quick note, numerical summaries do not fully describe the shape of your distribution. When we are trying to describe our distribution, you want to make sure you plot your data. All right, so we want to give a picture and a numerical summary to whoever is taking a look at our data. So here's just a quick summary of using the measures of center and spread. This one is approximately symmetric. Since the mean is equal to the median, we want to choose the mean and the standard deviation. If it's approximately symmetric, they're just your better ways of describing the data. Okay? If they're skewed right or left, like your two examples here, you want to use the median and the IQR. So remember, your IQR is stating the middle 50% of the data is from blank to blank. The standard deviation is the average distance from the mean is blank. Okay? Don't ever pair the median with the standard deviation because the standard deviation does not come from the median. It is calculated using the mean. All right, so just a quick summary. We learned that a numerical summary of a distribution should report its center and spread, so that's part of our SOCs. The mean and the median describe the center in different ways. So the mean is the average, the median is the midpoint of the values. When you use the median to indicate the center, describe its spread using the quartiles or the IQR. The IQR is the range of the middle 50% of the data, and that's how you're going to interpret it. Make sure that you show your observations for your outliers, okay? Your box and whisker plots don't extend to the boundaries, but they extend to the highest value of your data point before you get to the outlier. The 5-number summary just gives us a quick description and can be pictured using a box plot. Get used to box plot. We'll be using them all year. The variance and its square root, the standard deviation, are common measures of spread about the mean as the center. The mean and standard deviation are good descriptions for symmetric distributions without outliers. The median and IQR are better